each and everyone who has joined this meeting today. And I have the privilege to introduce the guest speaker of the day. I know him very well. Welcome, sir. Okay. Srinivas Rao Tatini, we call him short form as TS Rao. Uh, and his educational background is diploma in draftsmanship and design from British University, masters in public personal management from Osmania University, MBA in TQM and ISBM, and he holds various certification like lead auditor for ISO, EMS, QMS, OSHAS, IATF, PED, Dale Carnegie trained leader. He holds a Six Sigma Black Belt certified and certified global mentor, CIA certified green professional of carbon footprint and resource efficiency and environmental sustainability. And he is the proud owner of Foundrymen of the Year Award 2020 23-24. And he has got a vast experience of 39 years of foundry business experience in process including sand, centrifugal, GDC, lost wax, lost foam, and replicit with material during inclusion iron, steel, copper, alloys with hands-on experience and new product development. And the development over 2,000 products from drawing to delivery, which benchmarking performance with respect to yield, right first time speed to market. Achieve Green Pro and Green Co certificate for Madras Engineering with benchmarking performance, and AF Lost Form Council member support lost form duplicate technology development in India, China, Canada, USA, and Mexico. Traveled over 17 countries for business development, and let us see the organization he served. NPD head at Hinduja, Dr. Ashok Lal Ennur Foundries, Hyderabad, head of quality at Hindustan Motors Kolkata, head of NPD and MR at Dakshin Foundry Bangalore, head of NPD and process control in PT Castings, which is there in Hyderabad, director of Foundry Machine Shop and Global Casting Development and Armstrong Fluid Technology Bangalore, and chief operating officer in Madras Engineering Foundry Division Chennai, and is right now advisory at IIT Tirupati Superhuman Rise on Climate Change, Decarbonization, Geospatial Data, ESG reporting, research on composite material training, mentor and coaching. And I have the privilege to introduce the guest speaker, and it's my honor, sir. Now it's over to TS Rao, sir. Thank you.
Uh, Thank you, Mr. Yuvraj, for the wonderful introduction. Thank you so much. Thanks, IIF, for giving me an opportunity for the knowledge sharing. So, as always, we see, like, in the foundry business, so we need to learn from each other. So, there are books available, but they are little away from the practical experience what we have in the foundries, working in the foundries. So, always it is advisable for learning from each other, because no, we would have worked with hands-on experience. We would have failed many times, so that we exactly know how to fix. So without ignoring the theory, so as we know that the foundry is more like the common sense and the general knowledge. So with this introduction, let me share my screen so that we can get into the main content. Let me know you all can see my screen.
Yes, sir. Yeah, sir.
Okay, great. So, right. So we all know that there are various casting defects. We become sick of looking at in the foundry every day. If the defect is identified during the process, the impact is one. If the defect is identified during the dispatch, the impact will be 2. If the defect is identified at the customer location, the impact would be 10. Not 10 become 100. So always it is advisable to prevent the defect at the source. So you can see the various defects which are caused by the gating systems. You can see the shrinkage, misrun, inclusions, scab, right, whatnot. So there are hundreds of defects which are caused by the gating system, directly or indirectly, but gating system is the main source of the defects in the castings. So when you get into the next step, like introduction, we all know that the gating system is to create a channel for the molten metal to get into the casting cavity um, without turbulence by ensuring the sound casting. And the gating system is calculated depends on the material of construction. We should know what material we are going to pour in the foundry, and also depends on the molding process, is a green sand or a chemically bonded sand molding, or it is a metal mold, right? And also the quality requirements. The gating system also depends on the quality requirement, what we are expecting with respect to the level 1, level 2, level 3, level 4. And when you look into the objectives of the gating system, so it is expected to fill the mold cavity with the shortest time possible without turbulence. And we need to ensure the higher yield every time, optimum number of the pattern cavities that can be accommodated within the platen size. And we need to ensure that gating system gives a less rejection. And always we need to produce the defect-free casting. And we need to ensure the good surface finish of the product and less fettling or less rework of the product. And the gates should be away from the machining datums. If any gate, because of the over grinding or less grinding, the machine datums are likely to get affected. Always it is recommended to have the gating system on the tool point so that it get removed while machining. So, and geometry and aesthetics are not compromised because of the gating system. With this, in the next slide, what are the various inputs required for calculating the gating system? So when you look into the product requirement, we should know what is the metal of construction and beta of the liquid metal, what we are going to pour, the wall thickness of the product, what we are going to manufacture, the weight of the raw part, the modulus of the whole part, and also the significant modulus of the part. And also we should know the pattern layout, and also we should know the casting manufacturing process. When you come to the casting process, we should know what type of the molding casting process we are going to adapt, either it is sand casting, as a foam casting, or wax based casting, or metal based casting. Then in the molding process, we should know type of molding. It is a horizontal or vertical or incline, like the height of the pouring. And the look into the process parameters, we should know the pouring temperature, and also we should know the mold filling time. So you can see there are tables, a lot of tables available to calculate the modulus and also the significant modulus. Moving on to the type of gatings, there are two types of gatings as we know. One is the pressurized gating where the choke is very close to the casting cavity. This is when the choke is close to the casting cavity, it is called pressurized gating. When the choke is away from the casting, if the choke is near to the down screw, it is called non-pressurized gating. So the decision of to follow pressurized or non-pressurized, it depends on the molding process. And there are n number of formulas available for calculating the gating system, but I'm not going into the more details because every foundry is unique and everyone requires to follow their own tables for calculating the gatings. And this is very important. The gating ratios are very, very important. Whatever the formula you use for calculating the in-gate, but the gating ratios are very important. So the top table is for the typical ductile iron pressurized gating system. So down sprue is to offset, is to runner, is to in-gate. This is very important. So most of the foundry, they ignore offset, but according to me, the offset is very, very important with respect to producing sound casting. So that's why I introduced this offset. So normally they say 3 is to 6 is to 4, but I say 4, 5, 6, 3. This is very important. I explain why the offset is important in the subsequent slides. Going to the gray iron, for the gray iron, if it is a pressurized gating system, it is to be 0.9 is to 1 is to 1.3 is to 1. Again, the offset is very important. The offset should be either equal or little larger than the in-gate size. The gating parts, as we know, they are many parts which are used in the gating system. I explain you one after one. The first one is a down sprue where the metal enters to the casting cavity. The second one is a runner bar. If you see, the runner bar is tapered out to ensure that no, we increase the yield. There are calculations for the taper as well. Third one is a riser. Uh, for here, for this instance, we have shown this as a sand riser because of the William wedge, the shape what we see here. The fourth one is a riser neck. The fifth one is the ingate, followed by the chamfer for easy breakage. The sixth one is a flow ups and cup as per the process adapted. I have not shown the cup, but the pouring cup, it depends on the process what we adapt. That need to be customized, depends on the foundry process. So how do you select the feeders? There are many feeders in the market. How do you select the feeders? The first one is a sand riser where the MEF, the modulus extension factor is 1. The second one is insulating sleeves where the modulus extension factor would be about 1.5. The third one is insulating direct pouring sleeve. Here also the modulus extension factor is about 1.5. The fourth one is exothermic sleeve. Here the modulus extension factor is about 1.67 to 1.71. The fifth one is high density or neck down sleeves. Here the modulus extension factor would be about 1.75 to 1.8. And the last one is a chill. So the purpose of the chill is to push the hot metal towards the riser so that the riser will feed the required metal at the particular junction. So these are the feeders. The next slide, we talk about the filters. So the purpose of the filter is not only to filter the liquid metal, but also to ensure the laminar flow. Right, you can see that when the metal is poured before reaching the filter, you can see there is a turbulence, and after filter, there will be a laminar flow, and all the impurities in the liquid metal get trapped within the filter. When you look at the various filters, we have pressed extruded ceramic filters, and we do have ceramic foam and our honeycomb filters. The next one is fiberglass mesh. Mostly the fiberglass mesh is used when we tap liquid metal from the furnace to the ladle. Then within the mold or above the mold, we will use either pressed filters or foam filters. And you can see the various shape of the filter depends on your pouring cup and the filter print. You can use the various sizes. Moving on to the next slide is a basic gating design for ductile iron horizontal molding process. Here you can see the pouring cup, which can be customized, depends on the foundry process, followed by the down sprue. And there is a cup, it's called pouring cup or the well. And next one is a filters. In this case, we have two filters either side of the down sprue. Next one is offset. As I said, the offset is very important when the metal goes. Normally, when you pour the metal, we pour in the cope half, then it comes, this is a parting line. The metal comes to the drag half, then the metal get filtered, then clean metal goes and travel to the cope half. So that's why this offset is very, very important to ensure that there's no turbulence and the metal goes with a laminar flow through the runner bar. Then followed by runner and the ingates. Here on other side, you can see the chill. The chill pushes towards the riser where the riser get fed. Here in this case, it is a sand riser. And this riser neck is connected to the casting flange. These are the exothermic sleeves. You can see the sleeves are connected with a pipe. It get open through open through the roof. And we have flow ups. So there are three purposes for the flow ups. The first purpose is when we pour the hot metal, the gases which are accumulated within the mold environment, they are released through the flow ups so that there is no gas entrapment within the mold environment. And second is the first metal when we pour, that is likely to carry the loose particles within the mold. the mold which is mixed with the loose sand particles will get out first, then the clean metal gets in. And the third purpose of the flow off is whenever it requires a little pushback. So the flow off also can feed the casting as required. Right, with this is a very basic gating design for horizontal parting line sand casting. When you see the vertical casting process is again vertical green sand molding. Here we have, instead of cope and drag, we have SP and PP. But here the orientation would be different. Here the down sprue is the top, then followed by the filter and the risers on top of the casting cavity, the down sprue. And there are chokes here and the runner bar, then followed by the ingates. Normally the ingates are given in other halves. So if you see the typical layout, the cup here and then followed by the runner, then there are multiple cavities within the vertical molding. So in the vertical molding line, this is very important to ensure that no, all the cavities in the vertical environment are filled at the same time. So that is why the choke is very, very important. That plays a critical role to ensure that no, all three cavities, like there are three cavities in the vertical environment, all three should be filled at a time. So this is ideal way. Suppose if the choke is same, if the gating is same, then obviously the bottom one, because of the metallostatic pressure, the bottom cavity is likely to fill first, followed by middle and then top. So that is not recommended in vertical molding line. So moving on to the next slide for the last form technology. Here we have a lot of flexibility with respect to the gating design. There is no hard and fast rule like down sprue has to be here, runner here, ingate here. No, we are at liberty to keep wherever you like to have. In this case, we have down sprue at the center. There are two cavities, right? We can have runner on top of the casting, followed by the riser or the metal inlet. So you can, the beauty of the process is, down sprue comes the bottom. There is another runner bar at the bottom below both the cavities. Again, we can connect the ingate. Ingates can be connected directly, below the runner. So we have a lot of flexibilities in the last form technology where we can do anything. If you want to extend this, extend the runner, give one more ingate here. If you want to give ingate here, you can give. So there are a lot of flexibilities with respect to the last form gating because of the unique process. So these are the beautiful castings produced out of the last form casting process. And next one is a replicast process. Replicast process is same as the last wax investment casting process, whereas here, instead of wax, we will be using foam, which is very similar to investment casting process. Here also, we have a lot of flexibilities. We have pouring cup, followed by the large flow-ups, then down sprue, runner bars, ingates, right? These are beautiful castings produced out of the replicast process. Moving on to the next slide. This is for the last wax or investment casting process for the steel parts. Even here, we can see a lot of flexibilities. There's a down sprue here, the runner bar here. We can connect one ingate here, one more ingate here. See, there are connections between the cavities to ensure that they don't deform while pouring. So these are the beautiful castings produced out of the last wax process. So this is a nickel aluminum bronze. This is one of the toughest alloy to manufacture in the foundries. This is sand casting, but this is a pepsit three-part molding. So here you can see the pouring cup. There are two cups because of the weight requirement. So two cups are fed at the same time. And there's a couple of risers because the nickel aluminum bronze is a short freezing alloy. It requires a lot of feeders. And there are two down sprues. There are two filters, one filter here, one filter here, and they are ingates. So always for nickel aluminum bronze, the ingates has to be at the bottommost portion of the casting so that the metal flows towards upside. It is a beautiful casting produced out of the sand casting process, which is a pepsit. Moving on to the next slide. So these are for the copper alloys, but this is for the permold, or it is also called as a gravity die casting process. So here it is a direct, right, straight on the top of the casting we can pour. So this is pretty easy for pouring GDC. So when you come to the simulation, the first one is a filling. Always it is important. We can see that when the metal is pouring through the down sprue, how metal is flowing. So the symmetry is very, very important in the gating design. If you have two cavities, we need to ensure that all two cavities are filled at a time. If it is a vertical molding, if it is three cavities in a row in vertical direction, all three should be filled at the same direction. So it should be a replica. This is very, very important. So the simulation, the filling pattern will tell us how the casting is being fed, how the metal is going from the down sprue through the runner bars, and then how the casting is being fed. So we can see here the cooling mapping here on the right. The next slide is on the velocity. This is very important with respect to preventing. So is there any question? Okay. So the velocity is very important with respect to preventing the sand inclusions or any inclusions within the casting environment. Anytime the velocity goes beyond 1, so there could be some inclusions within the mold environment. So you can see in this case, everything is within 1. So this particular casting will be free from any inclusions. So here you can see the velocity mapping. The next slide is on the solidification. So the directional solidification is very important. The last freezing zone should be close to the riser to ensure that the riser is hot till the entire casting is solidified. So always this particular solidification pattern will exactly shows how the casting being directionally solidified towards the risers. It ensures that there is no hot metal left without feeding by the respective feeders. See, the last freezing zone is in the risers. Here you can see how the directional solidification is happening within the mold environment. The next slide is on the air entrapment. This is also very important. When I said that the flow-offs are very important, even if you have risers, it is required to have a flow-off through the riser so that the vacuum or the air which is within the mold environment has to be taken out through the topmost portion of the casting. So here you can see the flow-offs are connected through the risers. The flow-offs are connected on the topmost portion of the pattern. So here you can see is there any air entrapment. We can by the color coding. The next slide is on the voids. The voids also will happen because of the velocity or because of the air entrapment. Here you can see there's no voids. So the hot metal is laminar with a laminar flow. The casting, the hot metal is getting filled within the mold environment uniformly to ensure that there are no voids in the mold. So next one is a shrinkage process. You can see the shrinkage, the points are coming up when the part is getting solidified. So again, it depends on your the quality requirements of the castings. If you see the geometry at the cut section closely, this casting is well within the color coding of level 2. When it is 1 to 100, so for our understanding, we can talk, if it is within 20, it is level 1, with the level, if it is up to 40, level 2, if it is up to 60, level 3, if it is up to 80, it is level 4, if it is hot, red hot, then it is a level 5 shrinkage. When you see the color coding in the cut section, all are within level 2. So from here, we can find out the shrinkage pattern after the cut section. So these are the beautiful castings produced out of the good gating design. So for information, all these parts are developed by me in various foundries and various processes and various materials. I would like to give tips to the new product development team here because, in the Foundry, only the new product development team works on the gating design. And I know others also contribute, but they have significant role in the new product development because I worked in new product development for many years in many foundries. So this is, if you see the design of the safety pin. So when it is first designed in the 1849 through the 2025, so there is no change except a small change made after 1960 here. No change. Why? That means it is designed right first time and it survived centuries. So always the gating system also need to be designed such a way that it has to survive forever. So that is why I am adding some tips here for the NPD team to ensure that we survive for centuries. Always we have to be aggressive in first instance with optimum gating design. So any product which is being developed for the first time, we have to be very, very aggressive. Always we have to achieve very higher yield the possible. So if we can achieve 80%, 85%, always we need to try the best and aggressive gating design in the first instance. So later it is normally, some conventional foundries, they think like, no, we let us produce sound casting first, later we can improve as part of the content improvement, but it is very hard to implement because of the various reasons. The first one is a fear of failure. Suppose if you produce a sound casting without thinking of yield, any question? Okay. So when the product is proved, no, we get scared of correcting the gating system because no, we are likely to fail. If we fail, then the loss is going to be heavy. Like, the production get affected during the transition, taking trial again, going back to the original gating design. And, we need to engage a lot of resources for the trials, getting change again, trials, risk of mix-up. Then the parts are produced with the previous gating design and the current gating design, and they are likely to get mixed up. Then there will be a big issue later at the customer end. And again, cost of re-inspection, like, any gating change, it requires a validation, is a ultrasonic test or radiography test or MP test. So it costs money and no guarantee that no, we achieve same results. Suppose no, whenever we change the gating, it is my experience, we change the gating for the betterment. We conduct some trials, we produce some samples, we go back to the previous gating, but there is no guarantee that we end up with previous results. So this is a very unique problem in the foundries. It's not like no machining process that if you change the program, you go back to the respective process. No, this is one risk in the foundries. So again, no, if you keep altering the gating design, the rigidity and integrity of the tooling get affected because of many changes. And again, whenever there is a change in the gating system, it is expected to obtain the approval from the customer. Again, submission of the PPAP, lot of documentation work, and the production also get affected during this period. And again, identification and traceability of products produced with the various gating system. If you change gating system for 3-4 times, how do you identify the products with respect to the particular SAM? Then validation, expensive, numerous hours of work. And when you proudly say, I have improved my gating, I have improved my pattern yield by 78%, customers say, okay, thank you. So where is my compensation? Give me the discount. So this is another risk, right? That we would have seen. So here in the foundry, as I said, like, no, though the gating design is by the NPD department, but at the same time, we need to respect everyone's opinion. It's my experience in my past employment. We used to talk to everyone, right from the NPD through the fettling person. They give a lot of ideas. They say, why are you giving gating here? It is very hard for me to fettle. Why don't you move the gating to somewhere else? It also gives an idea, know how to improve the finishing process, how to improve the aesthetics of the casting process. So it's very important in the foundry. We need to respect everyone, every process in the foundry process. and never get satisfied with your work. This is very, very important, particularly for the new product development team. We should never get satisfied. If you are achieving 85%, we should target 90. If you are at 90, you should target 95. For the information of the team, my highest yield is 98.2%. So that is the highest yield I could achieve. So we should, even I am not satisfied. We should never get satisfied with our work. Always we have to work for the continual improvement continuously and with respecting everyone in the organization. So we are making somebody's life easy doesn't mean that we need to trouble other departments. So with this, I am concluding my presentation. So it's because we have some information through the slides. It doesn't mean that no, we are the experts. But every foundry is unique. We need to experiment with our given environment. So any gating which is very successful in a foundry, if you replace the same tool, if you move to the another foundry, it is not likely to give the same result because because of the various environmental conditions, we get different results. With this, let's all together make our nation proud. So thank you so much, team. So thanks for listening to me patiently. If you have any questions, I'll be happy to answer.
Sir, good afternoon. I am Satyanandan.
Hi, Satya. How are you?
Yeah, fine, sir.
Excellent.
As you said, the velocity is more important. It should be 1 meter per second.
Yes, it is one. Yeah, absolutely.
Yeah.
So
One doubt in this, is it common for both pressurized or non-pressurized?
this is for both. If in case of velocity, this is common for both. It has to be one. Beyond one always causes the inclusion defect in the casting.
Okay. So it is common for both pressurized and non-pressurized. 1 meter is
Yes.
maximum 1 meter
Yes,
seconds.
yes. That is why
Thank
the
you.
simulation is very, very important. During the simulation process,
Yeah.
like in the conventional foundries, we used to do a lot of trials earlier, but now we can do everything in a virtual foundry. We can do everything velocity, like filling patterns, cooling patterns. Everything can be detected during simulation process.
Okay. Thank you.
Thank you.
Sir, Bharat here from Grotech Enterprises.
Hi, Bharat.
In your slide number 7, you mention offset. I not understand about offset.
Okay, I'll bring this back again. Just a second. Hope you can see my screen. Not in the 7. I would have brought up here, I'll tell you. Okay. Here I can explain. Can you see my screen?
Yeah.
Okay. Though it is in the 7, but I will explain the purpose of the offset here. This offset is very important. See, because when the metal is poured in the top half, it goes to the parting line through the drag half. Again, there is a filter. In fact, this is my own gating system design. Like I have, with a lot of experiments, I have freezed this for the horizontal line. So this offset is important where the metal is expected to pass from the drag to the core.
Okay.
So this is always recommended. The area of the offset should be little over the down sprue, both together. So it should not create a turbulence here.
Okay.
So it should not create a turbulence here because of the sharp edges. That's why always the offset is important. Now, when you go back to the previous, like just a second. Okay. Here you ask the offset, right? Here, this offset. If you see the offset is little over the down sprue.
Okay, down sprue 0.9, offset should be 1. Okay.
1, yes, for the gray iron.
Sure.
For the ductile iron, if the down sprue is 4, offset should be 5.
Sure, sir. Thank you.
Okay.
Thank you, sir.
Okay. Thank
Sir, excuse me. I'm Foundrymen from Shantigate.
Yes, please.
Yeah. Actually, how much velocity we can maintain at aluminum bronze castings?
See, for any casting process, the velocity is one. That's what I said. So, velocity one, always ensure there is no turbulence within the mold environment.
Okay. Because why I'm asking, it is a more prone to oxidation during filling. So we faced a lot of pinholes after machining. So that's why I'm asking whether we can maintain one or below that.
See, there is no direct relation between pinholes and the velocity. Pinholes can happen because of various reasons. If any moisture environment within the mold, or if the metal is gaseous, right? Then we are likely to end up with pinholes. So there is no direct relation between velocity and pinholes.
Thank you, sir.
Okay.
Rao sir, one more question. Bharat here.
Yes, Bharat.
Related to high density sleeve, you said in your slide, one more slide, you have showed that we can provide a vent on the top of sleeve.
Yes.
So if I'm using high density sleeve, how I can provide a flow there?
So if it is a green sand, you can drill through the sleeve.
Okay.
Because what happens is the sleeve, if it is a closed sleeve, the sleeve
Yes.
contains some amount of gas inside, right?
Okay.
If you don't vent through roof, always the sleeves are expected to open through the roof, so that if any gas interrupted within the sleeve, that need to be taken out.
So high density sleeve also we can provide a vent, no issue.
Yes, we can drill. Yes, no issue.
No,
That is good.
If we'll provide a drill over there, then
Yes.
something change in their capacity of this one, high density sleeve.
No,
Maybe
it doesn't.
some
It
little
doesn't
bit
affect
temperature will.
No, nothing will impact. The modular sections in factory is very important, any of the feeding aids, because the high density sleeve will have about 1.8 to 1.85 the MEF. No, it will not affect. But always venting is very important to ensure that is there any gases which in the riser and the mold environment has to be taken out through the sleeve, because normally the sleeves are fitted at the topmost portion of the casting, right?
Yes,
And
yes,
beyond
yes.
that, there is a sand.
Okay, sir. Thank you, sir.
Thank you, Bharat.
Hello.
Yes, please.
Sir, this is Aravinda.
Yes,
sir,
Arvind.
I have one doubt. In gray in items, we are facing a gas log in top side in many castings. Let me know, sir, that the pressure head, how much we need to maintain the minimum?
It's not the pressure head. See, if that means, as I said, no, the flow offs are not open through the roof. That's very, very important. So, do we have flow offs at the suspect location?
Yes, sir. Yes, sir.
If you have flow offs, then you will not have any issue there. But you need to see the flow of calculations as well. The some amount of flow offs, if you have n number of flow offs on the mold, that should be equivalent or greater than the area of downsprue.
Okay, sir.
The amount of the liquid metal goes into the mold, so the same amount of gas need to be escaped through the mold, right? So if it is a green sand, because it is a porous, then it will get dispersed. But if it is a chemically bonded molding process, we need to maintain that at least 1:1 or beyond 1. Flow-ups are important in any molding.
Sometimes it's not enough, means we can increase flow of, correct, sir?
there is no harm in increasing the flow off, but at the same time, you need to see the modulus of the flow off. The modulus of the flow off should not be greater than the modulus, not modulus, significant modulus of the location where the flow off is connected. Otherwise, you will end up with shrinkage at the junction of the flow off.
Sir, normally I'm asking about gray in only, sir. In gray in, just some gas logs only available, not a sinkage we observed. When lot of castings, some void, big void we are observed. Maybe in
That
rough
is
casting also
very
not seen.
because of the gray iron, the characteristics of the gray iron, because of the expansion and contraction of the graphites. So there is no shrinkage. We don't expect any shrinkage in the gray iron. If it is a void, that can be eliminated with the correct flow, correct size, and the correct location.
Okay, sir. Thank you, sir.
Hello, this is
Yes.
Vishant.
Yes.
Sir, I have one doubt.
Yes.
Not doubt. I want any suggestion from you. Is there any recommended gating ratio for the last form process?
Good question. But last form is we follow the same gating ratio as I said, no, for the sand casting process. We can use the same, but at the same time, in the last form, we have a lot of flexibilities. We can play with the location, the geography, the geometry, right? We can do anything in the last form. So suppose if we have a shrinkage at the bottommost portion of the casting, you can connect the feeder, or directly you can give the ingate at the suspect location. So last form is relatively easy compared to the sand casting process.
Its flexibility is there, but if we maintain the lesser ingate ratio, then that tree strength will be get reduced. So,
But gating ratio, you please follow as I recommended.
okay.
No change in the gating ratio, but however, you can play with the last form gating system. You have a lot of flexibilities, a lot of freedom you have in the last form. But there are other parameters we need to be ensured, like the vacuum or the compaction, right? The grain size.
Yes.
Those are very important. Of course, the coating has to be breathable.
Yeah. Yes.
So we should not have more coatings, and glue is important. There are many other parameters which affect the quality of the last form, but gating ratio you can follow same as sand casting.
Yes, sir.
If you want, we can have one session on last form as well, because last form is
Please,
my
sir.
pet subject.
Please.
So we request your respective IIF.
Yes.
So yeah, you can request your IIF respective chapter. We can have one session on last form, because I am in AFS Last Form Council for many years. So I work with many foundries in other countries as well.
Yes. Okay.
Which foundry are you from, Vishal?
I'm from Mayura Steels, Kolhapur.
Oh, okay. I know. Yeah. Right.
Thank you.
Any other questions? Looks like we don't have any more questions, but I have one last question for you, sir. So is there any
Yes.
telltale sign that a defect is arising out of the gating rather than the process?
Sorry, Yuvraj, can you please repeat your question?
Is there any telltale sign that a defect is arising out of the gating rather than the process or the sand or the metallurgy? If it's
So gating is a sarvaroga nivarani. So what happens is there could be, in the foundry, it is hard to identify the root cause for the defect, but gating will help to mitigate the defects which are caused by the process. Like, suppose if we take a scab is not directly related to the gating, but however, the gating can help eliminating the scab defect. Similarly, the metallurgical defects. So gating is like sarvaroga nivarani. It helps. So that's why I said, no, whatever the defect, we can overcome by the gating design. but it
But
has
we
to
have to
be,
be careful.
properly verified. Vijayji, nice to see you here.
Yes, thank you so much. And so, shall I go ahead and give the word of thanks on behalf of the Chennai chapter and Bangalore chapter,
Sir, hello.
or do we
Hello.
have any further questions? Yes.
Hello.
Look like one more question.
Sir, good afternoon. This is Joshi Krishna from Bangalore Metallicals. How are you?
Hi, Joshi, how are you? Chennagidara?
Yeah, fine.
Okay,
I've seen you a
excellent.
lot of so many years. Sir,
Yes, good.
yeah. Sir, you told in this one 98.5 yield. For
Hmm.
which, whether it's the gray iron or edge iron or some other items.
Dr. Leharan, you are part of that. You are part of,
So,
I think you are there.
ah,
You are there with me. You are there with me that time.
Dakshin, dad
Yes.
pouring, I think. Correct, no?
You know that.
Yes.
98.2.
Yeah.
You are
Agree.
part of the team. Thanks for being there.
Yeah. So I remember that maybe direct pouring, I think that was the
Yes,
correct.
it is direct
Yes.
pouring. We pour directly on top of the casting.
Yeah, Kalpur. Okay.
It is, yeah, you're right. It is the cylinder body.
One more thing regarding is there any relation between dross and this one gating?
Yes. See, the dross is light in weight.
Yeah.
When the liquid iron density is 7.2, the sand weight density is 2.2, right? If they mix together, the density is about 3 and 4, right? So because the metal mixed with the dross, the density is low, it is always float to the roof. So that's why I said, no, the venting is very important to ensure that the dross goes away through the. First is prevention. As I said, like, first we need to have filters. So straight away you can use fiber mesh directly, when you are tapping from the furnace, you can, first stage of filtration, you can do at the ladle. And the second stage using the spot ladles, and then the removing the floated slag, right? And third one is a filter. The fourth one is the flow off. So step by step, we need to ensure that there is no dross or slag or foreign particles within the casting. So always we need to ensure that the casting is free from all these inclusions.
What about temperature role in this dross?
Yeah, see, the temperature plays a very critical role. The higher temperature also causes problem. Lower temperature also causes a problem. Always we need to establish the right temperature. Right? It depends on the wall thickness, depends on the mold filling time, depends on the how many molds they are expected to pour within the ladle. So that need to be established during the new product development stage. But however, we can do this experiment in the simulation. Why you should waste so many products for experimenting? We can do that in the simulation. Change the temperature, change the parameters in the simulation, see the result. Like you can keep doing any number of iteration till you get the sound casting. So as I said, always ensure that the right first time and highest yield first time. Later, it is very hard, very difficult for us to improve the yield because of the reasons I explained.
Yes.
That's what we did. That's what we did together in Dakshin. Always, probably that the yield used to be very high. I think 85 plus, if I remember.
Yes. And one more thing, if we use the filter and without filter, either a better metal velocity will get changed.
Yes, obviously. That's what I
How
said,
much maybe?
The purpose of the filter is not only filter the liquid metal, but also to regulate the flow.
Yeah.
Right? That you can see in the simulation. We don't need to ask questions. If you are simulating, you can exactly see with the filter, but in the simulation, we need to assign the particular portion as a filter. Then only the simulation software knows that there is a filter. Right? Then it changes the velocity. So the velocity is very important and the laminar flow is very important with respect to preventing the inclusion defects particularly. If it is a green sand, then it is very, very important. If it is a chemically bonded sand molding, still it is important
Okay.
because of the mold rigidity.
Much. Okay. Okay, sir. That's all.
Thank you, Joshi. See
Thank
you
you.
soon.
Thank you very much. Sir,
Thank you.
one more thing. Can
Hmm.
I share these slides afterwards?
Not not in public. We can talk. Anyway, we are in Bangalore.
Yeah, that's right. Yeah. I'll contact afterwards.
I believe it is recorded. I think we can take from IIF.
Yeah. Okay.
I think these are in some of the YouTube channels. Foundrybiz, they have this presentation. I think you can find in YouTube.
Okay.
Sir,
Okay.
good afternoon.
Right.
Good
Thank you.
afternoon.
It's Prasad from Growtech Enterprises.
Hi, Prasad.
Yeah, hi. One question from my side. For using filter, like for
Hmm.
ductile iron and gray iron, once we use foam filter, is there a chance of liquid slag going inside the casting?
Yeah, it depends on the particle size. So, the foam filters are better than the straight filters. But however, the liquid slag, because no, it hard to prevent through the filters. So that's why, the liquid slag has to be prevented in the melting process itself.
But true, this foam filter is having a honeycomb-like shape, so it will not be straight hole. While it passing through that, it will as a passes through the pores, it has to adhere to the pores cavity.
Yes.
What is the percentage of slag may go inside as per your experience, practical experience?
See, if it is a liquid slag, it is very difficult to prevent by the filter. About 50% of the liquid slag may get entrapped in the filter, but the balance 50% is likely to float along with the liquid metal. So always it is recommended to prevent generating of liquid slag. So always one of the parameter is the temperature. If the very high temperature, then it is like the liner is likely to get melted and then gets into the liquid slag. And there are many parameters that affects the liquid slag. Very difficult. 50% only we can prevent through the gating, but balance 50% we need to stop at the process, at the origination of the process.
Okay, thank you.
Any other questions?
Yes, sir. Yes, sir. Sir, one more question, sir, from Arvinda.
Yes.
Sir, recently we are facing about the white patches below riser. It is due to only the over rising or some other aspects, sir?
White patches.
Yes, sir. Only for the below rises only.
Did you cut and see the microstructure? What is the patches?
Yeah. Yeah,
What is
sir.
that?
The microstructure shows the flakes, sir, full of flakes.
Ductile iron or gray iron?
Actually, it is a GIN 700/2.
But we need to study the gating. So without studying, no, it's difficult. But always you follow the gating ratio, and I don't see any problem. No, if we have, I think we need to study the gating. We need to see the filling pattern, cooling pattern as well. Cooling pattern is also very important. So what we do is we simulate and see whether the directional solidification is happening, the cooling is happening as expected.
Yeah, okay. Okay, sir. Thank you, sir.
Thank you, Arvind.
Sir, again, Prasad here.
Yes.
Sir, we have typical issues of white patches in our housing castings. Because being in a hydraulic component manufacturer, anything depression or small holes that is not acceptable of a customer. in this regard, will you help us if we share the photos and this thing? So apart from this conversation, can we have a separate conversation and will you suggest something? If it's okay, then we'll have separate conversation.
Sure, sure, Mr. Prasad. Yes,
Sure, sure.
because I live in Bangalore, we can connect
Yeah.
sometime.
Okay,
Sure.
thank you, thank you.
Welcome.
Any other questions? I think we've had an interesting seminar when the question answer session is just as long as the technical part also. Thank you, Mr. TSL. On behalf of the IAF Chennai chapter and Bangalore chapter, I'd like to extend our gratitude and thanks for sharing a part of your immense knowledge to fellow Foundrymen. Thank you, sir. It was a very informative session with practical takeaways for the participants, from providing offsets to tips for NPD teams. It was very, very insightful. I would like to thank the IAF Chennai chapter and Bangalore chapter office bearers and council members who made this session possible. Thank you to all the participants who spent their valuable time, and we hope that you found some value in today's session. Looking forward to many more such sessions, technical sessions. Thank you again, Mr. TSL. Thank you so much. Hope you all have a happy weekend and looking forward to seeing you in the next session. Thank you so much.
Thank you, team. Thank you so much. See you all soon. Bye-bye.